All right. We're going to start going over lectures for, I think there's like 5 more lectures in the semester before the final. And so anyway, there's not going to be like an exam 4 and then a final. I just have like 5 more lectures to cover, and then we're going to have the final, which covers the whole semester. Okay. All right. So this is lecture 32. All right. Let's go ahead and do a review quiz from the last lecture. Okay, so again, we talked about KAs in the last lecture and how Ka is a equilibrium constant and what it represents, and that the larger the Ka, the stronger the acid. So if you look in for all 3 of these acids over on the table there, you'd see that the largest Ka is the dihydrogen phosphate. Okay. All right, water. So we've already kind of looked at some of these principles, and this lecture might be kind of a lot of information, but I'm gonna hopefully point out what's important to know. There's kind of a lot of like derivations for equations and stuff, which I think can be helpful, knowing why and where some of this stuff comes from. But I will point out kind of what you actually really need to know, kind of the meat as we go along. So don't be overwhelmed with all the different equations and stuff like that. If you're not getting it, just kind of sit back and wait for me to say, this is what you need to know, okay? All right. So water, we've talked about how it can act as an acid if there's a base in the water, right? So an example is like we put ammonia in water. Water can act as the acid. NH3 will accept a proton from water and become NH4, right? And then you're left with an OH minus. It can also act like as a Bronsted-Lowry base. So if we put an acid like carbonic acid in, it would donate a proton to water. This becomes bicarbonate, and we're left with hydronium ions as well. Okay, so then we have, so the name of this behavior where something can act as an acid or a base is called amphiprotic. Okay. So this is mostly just review from the last lectures. So here's an interesting chemical reaction that we're going to use to help us understand some of the properties of acids and bases and pH as we move forward. So let's say you put like water with water, which seems kind of dumb, but just go along with me for a sec. Okay, let's say one of these waters is the acid and one is the base. So this, let's say, donates a proton over to here. If you donate the proton, it's going to become a hydroxide ion. And then this water molecule would become a hydronium ion, okay? So this is kind of the dissociation of water in water, all right? All right, so this is that same equation from the previous slide. So this is always happening in water, okay? So water is actually exchanging protons constantly in a very small amount, okay? And you can see how when this dissociates, you're going to create the ratio between OH minus and H3O plus is 1:1. So there's always going to be the same amount of OH minus and H3O plus if it's just neutral water, okay? There's always some amount of this in the water, and this is a reversible reaction. So let's say we can write a equilibrium constant expression for this, and water is a liquid, so we're just going to have the concentration of OH minus times the concentration of hydronium. And Kw is what's known as the water dissociation constant, and it equals 1 times 10 to the negative 14. Okay, and you may remember that number, right? That was before we said that Ka times Kb equals 10 to the negative 14, right? Is it just a coincidence that that's the same number? No, we're going to go over why this is true, right? Before I just kind of told you this to get you by for that third exam. We're going to kind of talk about why here. So Ka describes this equation, and Kb describes this equation, right? So for Ka, we have an acid mixed with water. The acid gives up a proton. We have the conjugate base and hydronium. For the base picks up a proton from water. This is the conjugate acid of the base, and then we're left with hydronium ions. Okay, if we combine these reactions, so basically take all the reactants from both of these and put them together, we have these 4 reactants right here, okay? And combine all the products, and then start crossing out things that are the same on both sides. All right, so we cross out the HA, cross out the A minus. What we're left with is this, which is the same as the autoionization of water that we just looked at. Okay, so what it tells us is that Ka times Kb, putting these equations together, actually equals, let's see, Kw, right? So if you took the K for this reaction and crossed everything out, you're left with this, which is Ka times this, which is Kb, okay? So these two together are going to equal Kw, because even if you go further and cross these two out, and what else go and cross these two out, then we're left with hydronium times hydroxide equals Kw. Okay, this is the point at which I say all this means this, okay? Don't worry about all this too much. What you really need to know up to this point is that Ka times Kb equals Kw, which equals 10 to the negative 14, okay? That's what we need to know right now. All right, so Kw equals 1 times 10 to the negative 14. This is always true at 25 degrees Celsius. Okay, so pure water is referred to as neutral. So it has no acidic or basic compounds added to it, okay? And if it's neutral, we talked about how because of the stoichiometry, it's going to have equal amounts of hydronium and hydroxide concentrations, okay? So if we know these are equal, right, we could represent these as x and say x squared equals 10 to the negative 14. Do some algebra and we find that when water is neutral, so it has no acidic or basic compounds added, that the hydronium concentration and the hydroxide concentration are equal, and that concentration is 10 to the negative 7 molar, okay? Okay. So at this point, going over that slide, what I want you to know at this point now is that hydronium concentration is 10 to the negative 7 and hydroxide is 10 to the negative 7 when you have pure or neutral water, okay? So this is what neutral solution would look like. Okay, so Kw is equal to 10 to the negative 14. Again, this is always true at 25 degrees Celsius. It's still true when you add base or acid to the water, as long as you're at 25 degrees Celsius, okay? So the reason that this number is still true always is just that if you increase H3O plus, you're going to decrease the OH minus, but you're still going to have the product of these two equal to 10 to the negative 14, okay? You might be wondering why this is really important. We'll kind of talk maybe a little bit in this slide, but more as we move on to pH, you'll see why this is more important. Okay, so let's say you add an acid to pure water. Remember, acids dissociate and donate a proton to water, so they produce H3O plus. So your H3O plus concentration goes up, and your OH minus concentration will go down, because you can see that the OH minus concentration and the H3O plus concentration are inversely related, okay? Base does the opposite. It increases OH minus concentration and decreases the H3O plus concentration. So in summary from all that, all I really want you to know from that is that at a neutral solution, your H3O plus and your OH minus concentrations are equivalent. In acidic solution, you have more H3O plus and in a basic solution you have more OH minus. And that at any point, the H3O plus and the OH minus concentrations multiplied together times OH minus are going to equal 1 times 10 to the negative 14. Okay. All right. So this chart just reiterates that same idea. Okay. So in the neutral solution, these two concentrations are equal, and Kw equals 10 to the negative 14. Acidic solution, you'll have a greater concentration of hydronium to hydroxide ratio. But again, Kw equals 10 to the negative 14 for all these, doesn't matter. These concentrations can change and reflect whether it's acidic or basic, but Kw will stay the same. All right, we just have a few little quiz questions to hopefully help with homework and stuff like that. But yeah, that was a lot of information for not too much that you really need to pull from this lecture. Just kind of laying down some groundwork as we move forward. But let's go ahead and answer some of these quiz questions and apply what we learned. Okay, so this question says that lemon juice typically has a H3O plus concentration of 2 times 10 to the negative 3rd molar. What is the OH minus concentration in lemon juice? So here's where we want to pull out some of those equations that we learned, right? So we learned that H3O plus and OH minus concentrations multiplied together always equal 10 to the negative 14. Okay, so we actually know what the hydronium concentration is, so we can put that in here and then just solve for the OH minus. Okay, so again, Kw equals hydronium concentration times hydroxide concentration. If we're solving for the hydroxide concentration, which is what the question's asking us, right? We can rearrange this equation and then plug in Kw, which is always 10 to the negative 14, and plug in our hydronium concentration from the question and solve for the hydroxide concentration. Okay, go ahead and pause the video and try this one as well. Okay, so this says, what is the hydronium concentration now in a 0.10 molar solution of calcium hydroxide? Okay, so I think, initially it may be hard to understand kind of how to tackle this question, but just going off of what we've learned so far in this lecture, hydronium concentration times hydroxide concentration equals 1 times 10 to the negative 14, right? And the question's asking for the hydronium concentration. So we could say that the hydronium concentration equals 1 times 10 to the negative 14 divided by the hydroxide concentration. Okay, so we could figure out the hydronium concentration if we knew hydroxide concentration. What we know is that we have a 0.01 molar solution of calcium hydroxide. Okay, calcium hydroxide looks like this. When calcium hydroxide is placed in water, it is completely soluble, and it separates into calcium 2+ ions and into 2 OH minus ions. Okay, so if we have a 0.01 molar solution of calcium hydroxide, that means we have 0.01 moles of calcium hydroxide for every 1 liter of solution. It doesn't tell us how much solution, but that doesn't really matter because we're using concentration and we're given a concentration. So if we want to convert the concentration of calcium hydroxide into the concentration of hydroxide, all we need to say is that for every 1 mole of calcium hydroxide that's dissolved, we're going to produce 2 moles of OH minus, right? So now we've canceled out moles of calcium hydroxide and we're left with 0.020 moles of OH minus divided by 1 liter, right? Because the liter stayed. And this is the definition for molarity, right? So now we can say that we have a 0.020 molar solution of hydroxide. Now that is going to be our hydroxide concentration that we plug into this equation and solve for hydronium, okay? Let me back out and clear the slide. Okay, it gives us the 0.02 molar hydronium or hydroxide. We can solve for the hydronium concentration, similar to the last question. Okay. All right, go ahead and pause the video and try this one as well. All right, so this says 8.1 grams of hydrobromic acid are dissolved in water to make 250 milliliters of solution. What is the OH minus concentration? So this one, we're stepping back even another step further, okay? Question's asking for what is the OH minus, right? So we can take hydronium concentration times the hydroxide concentration. That's going to equal 1 times 10 to the negative 14. If we solve for hydroxide concentration, that's going to be 1 times 10 to the negative 14 over the hydronium. Okay. If we only knew hydronium, we could figure this question out, right? Because then we could figure out OH minus. Well, we're not given anything about hydronium in this question. So we're going to have to take a step back and see what's happening. So 8.1 grams of HBr are dissolved in water. Okay, so let's see. Let's just write this out. HBr is dissolved in water. Okay, what's going to happen? Well, hydrobromic acid is a strong acid, which means it's going to donate a proton, right? So if it donates a proton, we have Br minus, and we have H3O plus, okay? If it's a strong acid, it's going to completely dissociate. So we could say all 8.1 grams are going to turn into hydronium ions, right? So grams to hydronium doesn't really work, right? We always have to cross that mole-to-mole ratio. So let's use stoichiometry on this one. So if we have 8.1 grams of HBr and convert it to moles of HBr, so we're going to take the molar mass of HBr, so grams of HBr for moles of HBr. I don't know it off the top of my head. Like 38 or something maybe. I can't remember. 70, I'm not sure. Okay, now we can go from moles of HBr over to moles of hydronium, right? So if you balance the equation, it's just 1 to 1 for all these. So 1 mole of HBr for every 1 mole of hydronium, okay? And that's going to get our answer of moles of hydronium, okay? Now, if we know moles of hydronium, we can divide it by the volume to get the concentration of hydronium. Once we have the concentration of hydronium, we can plug it in here to this equation to get the concentration of hydroxide, which is what the question wants. So let me back up here. So again, we're going to convert from grams of HBr into moles of hydronium, or H+. Remember the same thing. Not the same thing, but as far as we're concerned, that's the same thing. Okay, so that gives us moles, and then we can divide it by the volume to get the concentration of hydronium. We can then plug this value in here, okay, rearrange, then plug it in, and we get our hydroxide concentration. Cool. Okay, so I don't think there was a ton of new ideas in that lecture, but there's definitely some different applications and kind of math problems to do for this lecture. So make sure to practice those in the homework and get help if you need it. And yep, we're going to continue moving forward after this and finish up acids and bases before the final exam. So, all right, we'll catch you next time.